Okay, hi everyone. We are doing a design review or discussion about category theory and its implementation in Wolfram language. And Jonathan has been doing a bunch of work on this, and this is his notebook. Oh my gosh, abstract quiver. Do I really start here? What?
I tried to vaguely conceptual order.
Okay, so let me just try to understand what is the. I mean, the principle here is, what does this roughly mean? Is this, yeah, go ahead, maybe.
So, I mean, the directed multigraph, right? I mean, that's all a quiver is. The thing that's significant about the quiver is that it has sort of essentially representation theoretic properties that means you can you can treat it as the underlying generating set of a category, if you like.
Is there, just as a syntax question, is there a way of specifying, I don't know what the terminology is, like in the version there, you're specifying the morphisms, but is there a way of specifying objects that don't have any morphisms?
Yes. So in the first argument, you can give a list of objects.
Okay.
It's I tried to make it as analogous to graph as possible. So the idea is quiver.
What's the difference between a category and a quiver?
Sorry?
What's the difference between a category and a quiver?
Right. So a quiver is, as I say, just a multigraph, right? It's just the reason for the name is that it's a collection of arrows. A category, you can consider a category to be generated by a quiver by you introduce this binary composition operation, you impose associativity and identity. So in effect, graph theoretically, you can think of it as being some generalization of a transitive closure operation applied to a quiver, along with introduction of self loops. Okay.
So I see. So the quiver is just a bunch of disembodied morphisms, basically.
Right.
And together with, go ahead.
Terminologically, in the framework, I distinguish between arrows, which are things that exist in a quiver, and morphisms, which are the things that exist in the category.
Okay. And so why is it the case that, by the way, did we invite Charles? Could somebody please invite Charles to this meeting?
Yeah, I'll ping him right now.
Again, he should have been on the invite list. I think he was on the invite list, but
okay. So I mean, another version of this would be something like directed edge. I mean, that would be why is that kind of not that would be sort of, seems like the natural way to represent in our framework one of these. I mean, perhaps that's two objects first, morphism second type thing.
Yeah, I mean, you can. I mean, if you give abstract quiver or abstract category just a directed graph, right, or a collection of directed edges, it will work.
Okay, let me just put this somewhere. Sorry.
Another point is, I mean, I assume in that model it has a way of having quote unquote anonymous arrows. I mean, anonymous in the sense it makes up a name for them.
Right. So it just, I think by default indexes them. It calls them, F1, F2, F3 or something.
So hold on. So if I put in that directed edge into a quiver, for example,
so you'd give it a list of, if you take
directed edges. Yeah,
if you give it a list of objects and then a list of directed edges, it should also work.
So I'll say X, Y, Z, and then a list of directed edge, X to Y, directed edge, Y to Z, G.
It may not pick up the names correctly.
Okay, so this thing there has a way of visualizing. So these things in general have a labeled graph.
Yep.
Oops, what's that? That doesn't seem, what is that? Why did that go blue, and why is this a Packlet thing? I mean, because that, I would have expected it to say resource function of abstract quiver there.
That generally happens with summary boxes produced by resource functions.
Okay, anybody understand that? Nick, do you understand that?
So yeah, that's what happens. A box head contains like just a symbol without the context of function repository. maybe it's hidden.
Okay, so I don't understand. That doesn't seem like the right thing. So this is probably Ian. Do you know anything about this? Anybody else know anything about this?
No.
Okay, so that seems like a function repository issue to be tracked down.
Well, so I mean, there's a trade-off, right? You can have the full context in the summary box thing, but then it appears everywhere wherever you have that summary box, and it looks really ugly.
You mean the resource function thing?
Yes.
Okay, somebody needs to look at this. Kristen, you need to take this to somebody who understands the resource system.
Yes.
And figure out what we want to do about this. Okay, so I mean, and there may be enough functions here that it may be that it wants to end up as a packlet of some kind. I'm not sure, but let's just understand what you've got here to begin with. So is this a formal symbol? This F1. This is a generated F1.
Yeah, exactly. That's why they've got the dots there. They're formal.
Right. I mean, I think that there's a piece of beautification that should happen here in terms of these actual diagrams. I'm not quite sure why it's such heavy font and all that kind of thing, but this is a minor issue. But I think we should have its fonts done, and perhaps I don't know whether these things always want to be black and white.
I mean, all of these design choices, I agree they're not optimized, but they were designed to make them look like, commutative diagrams that you'd see in a paper or something.
Sure, which they succeed in doing. So I mean, I think it's just a question of picking the fonts and so on. Yeah, so those are absolute sized of some kind. Okay, but let's just understand. So we've got this notion of these quivers, which are collections of arrows between objects. Now,
right. And crucially, the thing that makes this, again, a sort of an algebraic or at least a representation theoretic object or presentation theoretic object is that you can define relations, right? You can define relations between objects and you can define relations between arrows.
Explain.
So, I mean, I think if you scroll down, you'll see some example in the documentation. You'll see some examples. I think in the second example, I show some. So, okay, that's the simple labeled graph. If you go down a bit further, yeah, okay, there we go. There's an example of an equivalence opposed between objects, right? So, if you give the full labeled graph, it treats Z and W as being distinct. But if you ask for the reduced labeled graph, it will collapse them to one vertex.
Okay. Okay, so wait a minute. So first of all, we've got this collection of morphisms between these objects. And wait a minute. Why? Arrows. Right. So there is no transitive closure. It's just what you specify is what you get here, right? And there is no guarantee. I mean, okay, fine. All right. So now unlabeled graph, fine. Okay. Reduced labeled graph. Okay. So this is reduced with W and Z treated as equivalent. So those nodes have been collapsed into one node.
Right. Right. And so you can define relations between objects and you can define relations between arrows, as you see down in the next cells. There we go.
So what kinds of, oh, I see. So the relations between objects and between arrows are different arguments. And do they, is equal the only thing that they can take? Or could you say something, I don't even know what you would say. I mean, if you said to me, oh, F compose G is equal to, R compose Q or something like that.
Right. I mean, so obviously you can't do that in a quiver, but you can do that in a category, right? So you could give arbitrary compositions of arrows in a, you could make relations between arbitrary compositions of arrows.
Okay, but those relations are always represented as, compositions of things on either side and they're equal. Or are there other kinds of things you can say?
No, I mean, so equality is the only relevant predicate. Yeah.
Maybe you should also support two-way rule as a syntax for that. Does that make sense?
It does.
Okay, fine. Good. Okay. Okay.
And so you can see internally the quiver is just an association of objects, arrows, object equivalences, arrow equivalences.
Yeah, that's nice. Okay.
Can I ask, last time we saw an example where you could have an arrow equivalence that you could potentially deduce object equivalences from.
Right.
Does it do that now, or?
So not in the version that's deployed in the
It
function
just
repository, but in the version on the GitHub that's still the development branch. That is modified. So if you introduce an arrow, okay, first of all, if you introduce an arrow equivalence that's inconsistent, it will tell you, it will complain. And if you introduce one that requires an object equivalence, it will impose that equivalence implicitly.
Okay.
Okay. All right. So let's should we go on to looking at categories now?
Right.
Okay.
So
go ahead.
If you take that abstract category object and look at its association form, it may make it a bit clearer what's going on. Oh yeah, you can just do that. Yeah.
Oops, there's no. That's just an autocomplete missing.
Mm.
Oh no, it can't.
There's no way of
that.
yeah.
Yeah, I can't know that. Okay, it has its quiver.
Yeah, so every category is generated by so you can think of the quiver, the arrows in the quiver as essentially providing like algebraic generators for the category, if you like.
Mm-hmm.
Then you've got a composition symbol, you've got a symbol that represents identity morphisms, and then you've got lists of object and morphism equivalences.
This is nice. So now a question: if we put this into, axiomatic theory, like this format here, it'd be nice to have that compatible with axiomatic theory.
Right.
Which it almost is here.
Mm-hmm.
Okay, fine, I understand. So now what do we do with this? So this is now the category version of this, which has in addition the closure morphisms, so to speak, indicated here.
Right, exactly. So if you did a more complicated example, then you could also look at one of the properties of category include things like associativity equations and identity equations. You can see which equalities are effectively imposed by the axioms of category theory.
I see. So if I do that, do you have an example here?
If you just add one more arrow to that category you generated above in the notebook, then so if you make an arrow h from z to w or something, you can see an example of that.
Okay.
So then if you say category, associativity equations.
Out of curiosity, roughly how many of these sort of sub-values do these have? They have like 100 of them, or are they
there are loads. I mean, if you
okay.
ask for properties, if you say category properties.
There they are. My God. My God.
So is this most the functionality is in the sub values?
Well, yeah, I mean, each one of these is intended to be a very general function, right? So obviously abstract category has there are lots of things you might want to do with categories. So it has a lot of properties.
Right, right.
But yeah, as you can see, you can determine, when categories represent commutative diagrams, you can compute monomorphisms, epimorphisms, retractions, sections, endomorphisms, automorphisms. You can get zero objects. You can compute constant and co-constant morphisms. There's like anything you might reasonably, the plan was always any computation you might reasonably want to do with a category should be supported by abstract category.
Okay, that's cool. I mean, but now, okay.
Groupoid Q I want to optimize. Like the currently our handling for groupoids is not very good. I need to optimize that a bit.
So, for example, this would not qualify. I mean, a groupoid would be something much more.
Well, you can try and build one, right? So if you take, I mean, the minimal case would be something like if you had fx goes from x to y, goes from y to x, and then you impose relations that say, G compose F and F compose G are equal to the identities. That would give you a minimal example of a groupoid.
Okay, but so let's just try to understand some of these. Okay, so what we've got here, I mean, again, these are all very abstract category type stuff. And I think what you had started talking about is what happens when you go to more concrete categories where these Fs and Gs are actually are actually Wolfram language functions, for example.
Right, exactly. And in a sense, the idea is to use all the abstract stuff that we've developed so far to be a kind of skeleton for the concrete category framework, which is kind of where it gets potentially more interesting. Because in a sense, the idea would...
Yeah.
Sorry.
No, and just a very practical point. If somebody happens to just be able to ping Jeremy and see if he could just spend 2 minutes here and see if he can give us some specifications to make these, for fonts and things that would make these look more beautiful.
Yes, I'll ping him.
I mean, if he isn't available, so be it. But I just think this is so close to being really beautiful, but it isn't quite beautiful. Sorry, what were you going to say? So I think I get it. This is essentially sort of a labeled graph theory with transitive closures in it. And then you're asking for many properties of these graphs, which are, just like every one of these. I mean, we could imagine a world in which these were all separate functions, just like we can check for a graph, is this a complete graph and so on. You can check all kinds of things for this.
Right. I think the outcome of the last meeting we had about this was that we shouldn't do that in this case.
No, okay, fine.
Because there are a bajillion of them.
Right. I don't think we want to flood the function repository with 300 category theory functions.
Right.
It does seem to me though that this probably is more of a packlet than a function repository thing, but that's a different issue.
I mean, and right now, I mean, again, in the GitHub version, it essentially is treated as a packlet. It's just exposed through the function repository.
Yeah, which is fine. Okay, all right. So this is fine. So
this is a totally random question, but the composition, I'm not sure what symbol you're using, the circle dot thing. Is there a reason why you don't use like a Verarg's form of it, given that it's associative?
Well, it's because I want to be able to have the associativity equations as part of the, as an actual property.
Okay, I'm not totally sure. I don't know enough about when this would be used to understand when that would be useful, but sure.
Well, I mean, so there are situations in which you actually want to be able to track which identities are imposed by the associativity axioms versus which identities are imposed by the user, actually defining their own equivalences. And effectively, if we had a Vararg's form of, if we had an operator that imposed associativity, just by its structure, we'd lose the information about that's currently encoded in associativity equations, which is quite useful.
Is there any relevance to this application operator? It's a left to right. I don't know. This is probably irrelevant. I can't even remember how to use it. It's left to right function composition.
Wait, isn't that the same as at star?
No, it's not.
It's at star reversed, right?
Which is slash star.
It's
Otherwise
not that either.
Composition.
It's not that either. We introduced this. This was the original thing that, the combinator people were. This is what originally people thought was going to be the way to do function composition back 100 years ago.
But is it just a pure symbolic thing, or does it actually evaluate?
I'm trying to remember that.
This doesn't look like it evaluates. Has no built-in meaning. Okay, fine.
Okay. Fine. Yeah, okay. So, but Jonathan, you're aware of this, but it isn't relevant. Is that basically the picture?
I think so. I mean, there is the question. I mean, you brought up a slightly independent thing about whether you want to have notation for reverse function composition, right? Which is interesting and which does get used in category theory literature. Very often it's denoted with sort of semicolons and things. Okay. So rather than saying G compose F, you'd say F semicolon G. That's something.
Well, there already is. I mean, in case you don't know, there's composition and there's right composition, which are the two.
No, I'm aware, and that gets, and in the concrete category framework where these operators really are function composition in the Wolfram language sense, we use those.
Okay, well, let's take a look at this. So, okay. So fine. So we've got an abstract functor. My God, how many properties does this creature have?
Again, functors are pretty fundamental. So a lot.
My gosh. Hey, Jeremy, who just
Yeah.
joined. We're talking about category theory, and it's full of diagrams like this. Okay.
Okay.
Our mission is to make these look less ugly. Comments.
Well, labels versus the graph in the background are, how important are these labels? Because they seem really bold and large.
Well, they're the main event, really. I
Okay.
think it's fair to say. I mean,
You could lighten the graph then. I mean, you could go gray. Everything's black, and so if you had something lighter,
yeah, but I
something
think I
darker, it
mean
would help.
these fonts. I mean, Jonathan, can you say what the font is that you're using and things?
Not offhand. Hang on, I can double check.
It might be worth if you just go to Google Images and look up category theory or something, just to show some examples of how these are usually shown.
Let's take a look here.
I mean, maybe stuff like maybe making the letters, the objects less bold or something. I'm not sure.
I think they could be
honestly
smaller
bold.
too. They just seem oversized.
This is
Well,
just
it also doesn't help that this. Look at this. But these objects there. Oh, you are doing that as well.
Well, usually it looks like they have. It's usually it's uppercase, italic, and serifed, and not bold.
Yeah, so okay, I just checked. So right now we're just using vertex label style and edge label style directive bold 20. That's the only font information.
Okay, so I mean, this looks like a typical category theory thing.
Yeah, and that's more or less what I was trying to model.
So maybe we should just pick a non-bold and serify font.
Yes, and I mean, I think also they're using small circle for composition, and I'm not sure why we aren't using that, because that would seem like the natural thing to use, unless that means something different.
I tried it. I didn't like the way the operator seemed too small, but that may just be.
Yeah, but okay, so that might be a question of it's got to be other category theory.
Some people omit the operator altogether. They just write FG or something for composition.
Yeah, no, that's unacceptable.
Okay.
But I mean, this seems to be a typical, not very beautiful diagram. But Jeremy, what do you think in terms of? I mean, I agree that having a slightly different color for the characters and the arrows might help this look better.
Could we look at Jonathan's again?
Yeah.
And the labels are crashing. Some of these are okay, but some of them are crashing into the line. So space around the label so they don't touch lines.
That's a question of putting some. I mean, that's a question for the graph framework.
But I think you need to invent a way to scale. You can't. If you have a complex graph and you try to label everything and big labels, it's impossible. So, but on the other hand, what you could do is to use, tooltip. You can use a legend, so you don't have them right there, but you have sort of a reference to them where they apply.
Yeah, but I mean, remember, well, we'll see in the case of concrete categories what this is being used for. But I suspect, okay, there's a question of scaling the labels, for example, here. It could be done with scaled fonts. I don't know, it feels like even this would look better if there was slight grayness and possibly even some theming color. I mean, I don't know whether Jonathan, is there any kind of, I mean, look, for example, that person, that looks rather nice, having different colors for the
It does. My concern is just that there's no standard version of that, right? That the only notation that's even vaguely standardized is precisely the kind of pure black.
Yes, but that's mostly because people don't print books usually in colors other than black. I mean, I think that were they to be printed in some other color, people would just think they looked stylish.
Right.
Nobody would think it isn't a category theory because it isn't black.
Well, I mean, if you and or Jeremy want to invent a color scheme for category theory, I'm not going to complain.
I think we should. I think we should invent what I mean, relative to the physics project, for example, where because realistically, things like branch shield pink has been very successful. So my question is there only one kind of arrow here? Is that kind of an essence of category theory? There's morphism, purple or something, not purple, we've already used that, but it is, morphism gray or something like this. I mean, there's just, the arrows are all the same kind of thing, right?
Well, are you going to distinguish between arrows and morphisms, or ones that are compositional versus ones that aren't? I mean, how fine of a distinction should there be kind of chromatically?
Or do we want to distinguish between identity morphisms and others?
Yeah,
You
right.
could even imagine a situation where, like, the retractions or the isomorphisms or the monomorphisms get highlighted in a different color. As James said, there are many different levels of granularity you can imagine.
I think that seems nice. I mean, if look, here's the thing. These diagrams are pretty hard to understand in general. One of the things that we've been very successful with in the physics project is using color as a way to make diagrams easier to understand. So why not use that again?
Well, because the only issue is if there's epimorphism green and monomorphism orange. I mean, it's gonna look like a bowl of cereal, if you're not careful, right?
Right. No, I mean that's it's not going to work to have many colors. But the question is there, maybe there's one basic color. I don't know. I don't know this field well enough to know this. I mean, in this picture, these things that map things to themselves, what are those?
Those are the identity morphisms.
Okay. Where's there an isomorphism here? What's the defining feature of an isomorphism in these pictures?
So an isomorphism is one where, I mean, again, you can build one if you want. So an isomorphism is one which is a morphism which is both a left and right invert, or both left and right invertible.
Explain. So
okay, maybe it's again. I genuinely think it's easier to explain if we do an example. So if you build a category that just has it has two morphisms, one f from x to y and one g from y to x, let's say.
Okay.
Yeah. The morphisms just go both ways, right?
Right, but that's not crucially. That's not yet an isomorphism, right? So if you look at the reduced labeled graph of that.
That's a very bizarre message. Bug of some kind.
Reduced.
Labeled graph.
Labeled graph. Okay, so you can see there's now a G compose F and an F compose G. And a priori, then G compose F is not equal to identity on X, and F compose G is not equal to identity on Y. Right.
Okay.
So neither F nor G is an inverse of the other yet.
Right. Okay.
But then you could impose a pair of relations that says G compose F equals X identity and F compose G equals Y identity, which would make F and G equal to.
Okay. How do I say that?
So first, you want to put an empty list because you're not imposing any equivalences between objects. Then you want to put a list. In the first instance, you could just say circle dot G comma F equals over tilde of capital X.
F comma what?
Let's do G comma F. Let's do the X tilde one. Equals over tilde of X.
Okay. And then what?
Let's just check that works for a second. And so if you do the reduced labeled graph of that, you should see now. Yeah, so now that's collapsed to that. So if you ask for, say, if you asked for retractions and sections of that, you can see that G is now a retraction and F will correspondingly be a section, right? So that's telling you.
Why is G a retraction? What is the definition?
So G, that means that G is acting as a left inverse and F is acting as a right inverse.
Okay.
And so if you said like left inverses as a property, you can see that explicitly. So yeah, G is now the left inverse of F. Right.
Okay.
And so now if the morphism is both a left and right inverse, then it's an isomorphism.
Okay. Okay. This is all going to make, yeah, go ahead.
And so, for instance, okay, there's actually an automatic way that you can compute that. So in cases where you've got morphisms that go in both directions, but you haven't yet imposed all the relevant equivalences, you can request groupoid equations
Of this.
Yeah, and it will return the minimal set of equations between morphisms necessary to turn that category into a groupoid. In other words, to make every morphism an isomorphism.
Cool. Okay.
So that will tell you.
Ah,
Okay,
yeah, right.
F composed equals Y tilde. It's like how you can also request like commutativity equations, and it will give you the minimal set of equations between morphisms necessary to make a diagram commutative, which in this case happens to be the same thing, but in more general cases is not.
So if I were to take like this crazy puppy here,
Yes.
let's see, I can't pick up. Can I pick up this? Is this thing something I can pick up and do things with, or is that just a graph? Oh, that's just the graph output.
That's just the graph output. I mean, of course, you can put a directed graph back into abstract category or abstract quiver, and it will generate the free category or the free quiver from that graph. But whatever.
Okay, and hopefully you're going to include the labeled edges so that it will.
So that it correctly picks up the names. Yeah.
Okay, so if I take this and I take that rather slightly more complicated thing, and then I say something like commutativity equations here.
Exactly.
And by the way, that could autocomplete. Okay, cool.
And so then if you imposed those commutativity equations as relations between morphisms, then commutative diagram Q would return true.
Yep. Okay, so then let's just do that just for fun.
Mm-hmm.
So how do I add that to the category? How do I add those conditions to the category?
Wait, I think you picked up the wrong category there.
Oh, well, that wouldn't help, but okay.
But yeah, so in the same way as before, if after the
no, I understand that, but I'm asking from externally. If I've just got the category as a box, is there a way to add?
Oh yeah. So you can call abstract category of an abstract category and then impose new object morphism equivalences on it.
Okay, so then here you're saying these are relations between morphisms, so I just stick them right in here.
Yeah, you want to have an empty list first again.
Oh, for the objects.
For the objects, yeah.
Okay.
Now you can see commutative diagram is true in the summary box, whereas it would have been false before.
Okay, so if I now take that thing and I say full labeled graph.
Yeah, then you'll still because in the full graph you don't impose equivalences, right? That's what the full means. Whereas if you said reduced labeled graph, you'd see those directed edges collapsed back to.
Okay, why is this a commutative diagram?
Well, effectively because there are no multi-edges, right? So what it means, so graph theoretically, what it means for a diagram to be commutative, I mean, what you're saying when you say a diagram commutes, right, is you're saying that between any directed path between a pair of objects yields the same result.
Yes.
So in the reduced labeled graph picture, what that's saying, I mean, essentially that just reduces to a purely graph theoretic calculation of, do there exist multi-edges?
So wait a minute, if I say full labeled graph.
Yeah, then the fact that H compose G compose F and H compose G1 compose F and H compose G2 compose F are both edges from X to W. That is an indicator that this is not yet commutative if you don't impose any equivalences.
What would it mean to? I thought commutative meant it went backwards. What am I? I'm confused here.
No, that's not. So if you read a paper on homological algebra or something, and it says this diagram commutes, what it means is that if you start at the top left and you end at the bottom right, all directed paths between those two objects yield the same result.
Is that like confluence?
It's not really.
Why not? Because all paths from, you're saying all paths from anything to anything, there are always paths. I'm confused.
No, I think it's not a statement about the structure of the graph. It's a statement about if you follow the arrows.
It's an algebraic statement. Yeah.
Yeah, it has the same effect because these are mappings, right? These are functions.
Exactly.
But how do we?
I could draw a category where I've got, I could have a thing of one edge is sort of like the +2 operation, another edge is the ×2 operation. That doesn't commute, but I can still draw that diagram.
Right.
So, okay. So I think this is going to be clearer when we actually go to concrete categories, which hopefully we're about to do.
Mhm.
I have a question, quick one. It's like, I usually underneath you just simplify with assumptions in order to reduce all of those inequalities. Like for all the paths from every pair of objects, you like assume all of them and you simplify an assumption, something like that. Or how do you do the reduction?
You could think of, I mean, yeah, it's effectively like a simplify with assumptions. There's a very, very minimal theorem prover that's effectively the core of this that does those, you know, it does the finite model theorem proving case that is effectively like a simplify with assumptions.
How does it, I mean, is it algorithmically sophisticated at all, or does it need to be?
For the handling of universal properties, it needs to be somewhat algorithmically sophisticated.
But I mean, in practical uses of this, you know, the category diagrams people draw in books are tiny, like these. But
right.
Is there a practical use where you have a category diagram with a million million objects in it and things?
Sure.
Okay. Does anybody use those in current? I mean, other than the kinds of things
people don't draw the pictures, right? But most categories are infinite.
Yes, but I know. But
I mean, a million is large, but I've never seen one with even 100. Jonathan, what's the largest category you've ever seen, like in the literature, that's actually drawn out? Maybe in terms of morphism count.
It's important to note that when people draw diagrams, they're usually not drawing the entire structure of a category, right? They're drawing an indexed family of objects and morphisms, usually. But yeah, I mean, the largest commutative diagram I've ever seen was in a paper by Lurie that like spanned like 2 pages or something. And that was viewed as kind of obscene.
What was it about, and what kind of a thing was it?
It was some coherence condition for a higher topos construction.
Okay. But so you can think of that as defining, in some sense, these are like equations, but this is a kind of a notation. How should we think about this? I mean, go ahead.
I mean, there's a nice phrase in McLean's book where he describes commutative diagrams as like commutative diagrams are to categories what equations are to algebra.
Okay. But so,
I mean, it's kind of a very compact notations to give a huge potentially large number of equations.
Yes. Yeah, exactly. I mean, as you can probably tell, you don't have to grow these things very large before the output of commutativity equations gets very big.
Well, so if wait a minute, what did we do here? Did we have commutativity equations there? Okay.
Do you find things like cycle bases and things to minimize the number of equations you have to list?
No, but that's an interesting optimization. No, I mean the way that it's effectively done right now is we find a set of equations and then we do algebraic simplification on that. But then maybe it'd be interesting.
Using what? How? I mean, using. How are you doing the actual simplification here?
Like I said, at the core, there's like a mini equational theorem prover.
Okay.
That does the simplification, amongst other things.
So cycle basis is a way to, well, enumerate the basis for all the cycles.
Mm-hmm.
But so, yeah, right. So, I mean, but if we thought about this in terms of algebraic equations,
mm-hmm.
What would be, I'm just trying to get a sense of it's saying W is equal to this. Yeah, I see. I mean, okay, fine. So we could write out this whole diagram as a bunch of equations that, H of Z is equal to W and so
on. Well, it's yes, I suppose.
I mean, that's effectively what is going to happen when you make these.
Yeah. And so right now, because we're dealing with the finite case, the theorem proving that goes on here is quite simple. But if you pull up a version involving universal properties like pullbacks or push-outs or something, then you see a slightly more interesting, slightly more sophisticated version. And maybe if I show the limit later. Sorry?
What should we look at here?
Look at pullbacks or something. Or I don't know. So if you look at the universal property a little bit further down.
Okay, we've got another
here you-
line. We've got another type of line here. I was gonna say, is Jeremy's involvement done now? And no, we've got another kind of line.
But again, this is the standard notation for how a universal property gets denoted, is to use dashed lines.
Okay. Well, anyway,
So
yeah.
So whereas before we just had diagrams that represented purely algebraic equations, this is now a diagram representing a universally quantified formula.
Why is there a uniqueness thing there? That means there exists unique that, or
Isn't
does
that
it?
the point of pullbacks? That there's a unique one.
Okay, but I don't understand. I don't
We need to review pullbacks, probably.
Yeah, I don't understand any of this.
Sorry, wait. Well, I think I dropped from the call for a second. What happened?
We were discussing pullbacks and the fact that I don't understand what they are.
Okay, maybe it's easier to start with products then, because products are like baby pullbacks.
Okay, but I just let's let Jeremy go. If I mean, Jeremy, do you have any immediate comments about this, the visual stuff that
Not yet, but I can work with, whoever. I'm not sure who I'd work with, but I'm happy to jump in.
Well,
by the way, just before, if Jeremy, if you're about to go, I just sent you, or I sent Stephen you a screenshot of I just tried changing the fonts and stuff a bit.
Oh, okay.
Let me just bring that up. Help. Why did this not come up?
I don't see it, Christopher.
I just sent it to SW Wolfman.
Okay.
Yeah, well, that looks very much more like the textbooks. I'm not sure it looks. I think we need something stylish somewhere in between these. Jonathan, what do you think? I mean, that looks very textbooky.
It does. I mean, at the very least, I think we should support that as an option.
Mm-hmm.
But I think what we want is something in between that is stylishly, and I think here it becomes clear that this thing is really pretty oversized, and maybe the
maybe circ or something is better. The circle composition.
That won't work because I had to install the LaTeX font.
Oh, I see.
I didn't know what font. I mean, I assume we have a LaTeX looking font already somewhere because we use it for the LaTeX stuff, but I didn't know what it was called.
Right. Okay.
One concern I have is when you actually have the full labeled version, which we can see with this pullback example, when those are labeled, those labels become obfuscated. I mean, that's a general design challenge.
That's something more for graphs, and that would be something where we want those to be call outs with arrows to the arrows, more or less.
Ooh, including additional arrows that aren't, categorically meaningful would be, I don't know. Doesn't seem because it's like
I don't think you can draw an actual arrow. I think at best you can have a tooltip or something.
Yeah, I think tooltips is not a terrible idea. Like, I mean, that's what we do with the with proof graphs, right? Is like when they reach a certain size, we no longer print things on the graph itself. We relegate them to tooltips.
Okay. Anyway, so minor things to be done here. We need the color of morphisms, so to speak, or the color of arrows. I think we should pick some color that is something.
And I would argue there should be consonance with the multi-way color scheme.
Yeah. Well, what should it agree with there? Should it agree with the edges in the multi-way graph? Because
in the concrete case, right? Then these edges are the edges of a quiver are precisely evolution edges in a multi-way system.
Fine. So then it's probably then we got a color. And then
but those are arrows in a quiver. What happens when we actually introduce compositionality? Should they have a different color or not? Right.
We haven't, until the CT framework, as far as I know, we haven't looked at the compositional structure of multi-way systems in that kind of way.
Mm-hmm.
Right. So perhaps the right thing is we have a slightly different color that can be, a cheerful color of some kind for the actual transitively closed, whatever,
For morphisms as opposed to arrows.
Yeah. But I think it's nice. I think as a first order thing, I think it'd be kind of nice to see, the underlying skeleton, the arrows from the underlying quiver in a kind of multi-way color, and then all the extraneous, all the additional arrows, with as you say, some jolly but different color.
Fine. Got any basis for colors here? Any way to pick a color? What's the color of? I mean, what will be any kind of like trees we made green, okay, for obvious reasons. Anything other than yellow math books and things? No. Okay. All right. Well, separate problem. All right. We should let Jeremy go because we're going to go on and talk about. Look, I really wanted to get to this concrete categories business because it looks like there are a lot of lovely things with these abstract categories. Sure. Is there stuff
I do think it's worth seeing just because that's quite different to the other stuff we've talked about. I think it's worth seeing an example of a universal property and an example of what these monoidal categories can do. Okay. Because they're in some ways the two.
Do you want to share? Do you need to share, or can I see?
It's up to you. If you think.
Well, I mean, where is?
Well, so again, if we start by looking at abstract products, maybe that's easier than looking at abstract pullback straight up. So here's a minimal example of a universal property. So what you do is you take, if you like, one way you could think about abstract the way I like to think about categorical products is that they're like vast generalizations of the concept of set intersections.
Okay.
So if you imagine A and B here are sets, if you imagine all the objects are sets, and if you imagine all the arrows are essentially inclusion relations between sets, then if you think abstractly how you would define the notion of set intersection, the intersection of sets A and B is the set such that A intersection B is a subset of A, it's a subset of B, and crucially, it satisfies a universal property in the sense that any other set that's a subset of A and a subset of B must be a subset of A intersection B.
Yep.
Right. And that's precisely what this universal property describes. So if you scroll down and show the universal property, so here, that's exactly what we're seeing, right? We're saying we've got this A product B, we've got these projection morphisms pi1, pi2 into A and B, and then we're saying for any Y such that, and for any F1 and F2 such that Y injects into A and injects into B, there exists a unique F from Y to A product B.
Okay. Mm-hmm.
And so then internally, if we scroll down a bit more, more still, there we go, universal product equations down there. Internally, that just gets translated into some first order logic that we can then do theorem proving over. So then this product is just like a disembodied thing that you can then embed into some arbitrary category. And I have some examples of that later on in the documentation. So products are, as I say, like a sort of vast generalization of set intersections. Co-products, which are their dual, are like the generalization of disjoint unions.
Mm-hmm.
And then, I think the last example in this, in the basic example section, shows, here we're embedding. Here it's showing how you take a product and you embed it into some pre-existing category, and in that, when you do that, suddenly it takes this abstract, universally quantified universal property and it actually instantiates it on the objects and morphisms of the category you embedded it in.
Okay. I really need to see some applications of this. I mean, this is lovely. And by the way, I mean, this is to me, this is super helpful to see these things in this somewhat concrete computable form, as opposed to just seeing pictures in books.
Right.
And it seems like anybody who's teaching a category theory course should be using this type thing.
I agree. But so products, co-products, pullbacks, push-outs, equalizers, co-equalizers, limits, co-limits. These are all examples of constructions with involving these universal properties. So if ordinary diagrams are like equations in algebra, then these universal properties are like universally quantified logic expressions.
Okay.
Or universally and existentially, crucially. I mean, they're both quantifiers exist.
Okay, let's talk about concrete categories if we could. And I think
Sure.
you've got open questions here, which, oh my gosh, connections to the pure math packlet. Now, Ian might be able to speak to some of that.
Right.
Ian, can you speak to any of that?
Yeah, we met. The separation axioms for topological spaces may be able to be characterized in terms of universal properties, but it's something we'd actually have to use some creativity to think of how to encode all the different properties strictly in terms of universal properties.
But I mean, in our representation of pure math, can we do an example? Can we pick up an example here? Is there some random example where I can see relations between certain, I don't know, properties of topological spaces or something?
Yeah, can you like do needs of pure math backtick? And then do entity topology concept, comma, is T1. There's no autocomplete.
Topology.
Topology concept
Okay. And then
is T1.
T1 like this.
And then get the property summary grid. This is like the standard definition of a T1 topological space. You say every singleton set is closed.
Okay.
You could rephrase this in terms of what kinds of morphisms exist between appropriately chosen objects. And so the task would then be to take every concept that we have, at least for separation axioms, and come up with what those clever
Sounds to
diagrams
me like this is a great project for somebody who's like doing classes in this stuff right now. I don't know, why am I thinking of Mano somehow?
Jonathan put a link in chat of some examples of this, but it's by no means exhaustive.
Yeah, so essentially there's a universal, if you consider the category of topological spaces and continuous deformations between topological spaces, there's a way you can represent things like these separation axioms purely in terms of universal properties on these diagrams. And so then one possibility is that we might be able to so some of the kinds of deductions that right now are kind of more or less baked into the pure math, more or less hard coded into the pure math packlet.
Mm-hmm.
We may be able to automate more of them, or at least that would be the sort of optimistic hope, if we were to encode more of the assumptions in this category theoretic way.
Well, so essentially, it's a higher level version of theorem proving, where you can make statements about things which are stated in terms of morphisms and so on, using essentially, some kind of diagram, arrow chasing diagrammy type thing. Is that the idea?
Yeah, exactly.
So you'd be able to, the concept would be that just like at the level of sort of find equational proof, you're dealing with theorem proving at the level of, F, A dot B dot C equals C dot B dot A or something. Here you'd be able to state things in terms of what kinds of statements would you be able to deal with? You'd be able to say this, I don't know, what would be an example of a kind of thing you would be able to establish like that?
Well, if you could construct these, if you had a way of representing these concrete categories of things like topological spaces, then in principle, you could prove, any statement in topology.
But so, just so I understand, is there a sense in which there is sort of an axiomatic basis for topology represented in category theory language that then has some laws of inference that are based on sort of diagram chasing or whatever?
Yeah, exactly. Except it's not an axiomatic, or it's not, just in terms of the nomenclature, it's not referred to as an axiomatic basis, but yes.
What is it? What's it called?
Well, I think ultimately this goes back to the thing you were commenting about Saunders-MacLean and, category theory being a sort of non-axiomatic thing. But yeah, but so people would just say, a categorical or a category theoretic formulation of some mathematical field.
But what's the foundation of that? So you write down, like for topology, do we expect that there's sort of, 10 lines of stuff you write down to define that, or do we think it's, what is that?
Yeah.
What is the? Go ahead.
Well, so the categorical description of, or the description of top, the specification of top, is, I think you can write down in sort of four. I've seen it written down in 4 or 5 rules, so kind of comparable to the size of the standard axioms of point set topology.
I think we have it in the pure math Packlet.
Okay,
Like the entity list of category.
Sorry, enter the
Yes,
list.
you do. You do. I remember that. Yeah.
What should I do here?
Of category, the string category.
Don't I need to say what the?
Isn't it topology concept? Oh no.
That should have worked.
Did it not load up the entity store correctly?
Oh, this might be hidden behind a flag for unreleased functionality.
Can we?
The point is, like, we define categories the same way we define topological spaces. And
I'd really like to see this. But how can we get this
can I
somehow?
share, maybe?
What's that?
Can I share my screen?
Yep.
Stephen, I mean, you can see quite easily how you could define it, right? So there's a very obvious category theoretic formulation of what it means to be a continuous function, right? You can very easily state, pre-image of any open set is open, but if you have a pre-existing category of open sets, right?
Yes.
That's just a statement about that's a pure function composition statement. And then if you make this statement that any continuous function is a morphism in top, then that's sufficient to define top.
Okay, so wait a minute. So what are we seeing here? So we're seeing here. Okay, so I mean, clearly the question for Jonathan and so on is, could we just take things like this and make non-trivial deductions in topology, for example? What is
Yeah,
it?
I mean, that's why we had this meeting. It's, I mean, that's why Ian, Jack, and I had this meeting to
Okay.
sanity check whether that was a useful thing to do.
But so do you see that as being part of your concrete category effort, or this is, I mean, because it seems like this is just filling in what F and G might actually be.
Well, I think I kind of view it as being a slightly orthogonal direction. That, in a sense, actually, what this is more like is this is more like having a category repository, right? Where, because the concrete category framework is essentially taking, you take some specification of a multi-way or a multi-computation and you build a category out of it. Now, of course, you could do that with topology or whatever, but somehow that doesn't seem like the right thing to do. What I would argue is potentially more fruitful is to have a repository of common categories like set or top or whatever, have them be represented purely symbolically, and then do automated reasoning over those.
That sounds interesting. I mean, it sounds like doing like theorem proving, but at a much higher level.
Yes, I mean, so in a sense, the framework right now is a theorem prover, but also a theorem discoverer. Right? So it does. I mean, you can both enumerate things that are true, and you can prove that they're true.
But the enumeration of things that are true is a question of certain properties of. I mean, you're making algebraic certain things that are based on tracing paths in those graphs. Is that true?
Well, in the trivial cases, yes, you can do that graph theoretically. But for things like, for anything non-trivial, like anything involving universal properties or anything involving functors, you can't do that.
I see. But so you believe that there's a way of enumerating true theorems. I'm not quite yet clear how to do that. I mean, in the case of in the case of equational kinds of formulations of things, we understand how to just use substitution or something to derive new theorems from old ones. What's the analogous mechanism here?
Well, so as you say, in the pure category case, it is essentially just you can just do it through some graph theoretic means.
Okay.
In the more sophisticated cases, you have to fall back to standard equational theorem proving methods.
on constructs which are like the constructs that Ian is showing us here. Is that right?
Right. You're doing equational theorem proving on morphisms and compositions of morphisms.
Right.
And there's multiple levels of theorem proving you might want, like proving the actual theorems of topology from the axioms of set theory. And then there's things like proving relationships between different kinds of topological properties that might be able to be done in terms of like diagram chasing universal properties.
So in this diagram here, were you able to already establish results from this? What is this diagram? This is what depends on what, is that right?
No, so this is topological properties. So if two spaces are homeomorphic, then they will the property depends on equivalence classes. Like, so whether or not something's a surface depends only on the topology of it, not the particular.
Yeah, what is this
set.
diagram showing? This is showing the dependence. If it's, is regular,
If there's
is
edge,
for example.
yeah, like they're direct implications. But the point is that there's more relations here than just direct implications. This is like a subgraph of
Okay,
some
but
kind
so
of.
what would something like is regular? What would that turn into in the category theory framework? That's not a morphism. That's some other. What the heck is that?
Oh, no, but that's why.
It's like that link that Jonathan sent. Like even saying something is T1, you have to say, oh, well, I'll give you a particular object and then give you relations that exist on the morphisms between that object and your space.
Yeah, like I said, they're universal properties.
The whole tower of these things to get to the more complicated kinds of properties.
Each of these can be represented, or at least the majority of them, as far as I'm aware, can be represented as universal properties. And as Ian said, that's kind of why I sent through that link.
Okay, but so
the point is that one is doing theorem proving at a higher level than just grinding everything down to the axioms of set theory, right? You're doing a kind of more synthetic mode of reasoning.
I could just say is Hausdorff and conclude a bunch of things without needing to actually be able to generate set theory proofs, because I know the ontology of these properties.
Right, but this is captured. You have a way of capturing this, which is sort of your set of implications from these properties, which is yet a separate way of thinking about how to store this kind of mathematical knowledge.
Like
right, but
being normal equivalent to being T1 and T4, that kind of thing.
I understand, but this is a set of implications. So what we've got is we've got the category theory way of thinking about it. We've got the set of pure implications between properties, and we've got the low-level kind of algebraic way of thinking about it in terms of raw, variables and axioms of set theory and so on. Is that a fair statement? I mean, what's the relationship between this level of implications between properties and the category theory level?
I mean, I can say it for a third time, but like these can be captured as universal properties, and then one can deduce relationships between those universal properties, right? So the idea would be again, the reason we had this meeting, Ian, Jack, and I had this meeting was to discuss whether it was feasible to be able to deduce these, this collection of implications that essentially that graph Ian was showing was representing from the underlying category theoretic representation of these things.
When you said universal property, that was the dotted line thing in.
Yes. Yeah, the analog of universally and existentially quantified propositions. So like in that NLab article, you can see the T0, T1, T2, T3, T4 separation axioms encoded as those universal properties in top.
Okay, but when you say, I mean, just for my understanding, so there's morphisms which are solid arrows, and there's universal properties which you're saying are like that, except they're dotted arrows.
Well, no, the dashed arrows, as we saw before, are the uniquely existentially quantified morphisms in that picture.
No, I get it, but from a graph theory point of view, we are adding in certain dotted lines.
You can have universal properties that don't have existential quantifiers in them. You can have universal quantifiers, just pure universal quantifiers.
Yeah, I think there's more I need to understand here, but I'd like to. But I mean, so the bottom line here might be that using, for example, the things already curated for the pure math framework, it might be possible to make an assertion in terms of in terms of those properties that Ian was showing there, and prove some assertion that is not deducible purely from the implications that are listed in, that Ian has already curated. Is that a correct statement?
Or even just to be able to validate the ones that are already, or automatically generate the ones that are already there, even if we don't discover new ones. It'd be nice to have some way of.
Right. So this graph is from the point of view of I just curated all of these. I just trust these are true. I don't have proofs for any of these, right? And then I want to prove things about particular spaces given this huge collection.
Okay, so your claim is that
this thing is a path toward actually being able to prove things like this, and maybe even because sometimes I'll try to figure out, is a space paracompact when I know that it's countably paracompact, and I won't have a theorem for that. That might be a path if we had universal.
Right. So you're saying, given the definition of top, the category theoretic definition of top, and given, I don't know how these properties are defined in terms of top, for example, is Lindelof, does that turn into some whole sort of statement in terms of morphisms and things inside top? How does that work?
Yeah, let me pull that up.
Oh, so it is already.
Yes.
I think it had one F. I think it has one F. I mean, I just read it off that other place. So, okay, but so that's fine. That's in words, but can we see that in more? Oh, wow. Okay.
So yeah, it's for every object in the category, you make some statement about it. And the claim is that
open cover of now being
written as a universal property.
Say that again.
The claim is that this could instead be written as a universal property instead of in terms of like these are all basically set theory constructions.
But that label is open cover of. Is that being defined by this statement, or is that have to have some other separate
concept is open cover of? This is what it means to be an open cover. You have a collection of open sets whose union is the.
Okay, so there's certain base concepts here. And are those base concepts somehow defined in the category top, or are there base concepts that have to be introduced?
No. As I say, these can all be represented purely as universal properties. So like an open cover is just an epimorphism with some coherence conditions.
Okay.
And what I have now, top itself is defined in terms of set theory, which is itself not defined by this project.
I understand. So just so I'm understanding how things fit together. I mean, in the kind of proof assistant world and the homotopy type theory world, how does this relate to what we're talking about here? I think
I'm not entirely sure what it is we're talking about here. So,
well, I mean, what we're talking about here is encoding. You're saying category repository, okay? And it seems like we've got a couple of components here. We've got a category repository that has the definitions of these categories. We've then got Ian's thing, which is defining a bunch of human relevant properties, which can be ultimately defined in terms of the primitives of those categories. Is that a fair characterization?
Yeah, but obviously that should be part of the category repository. I mean, just having a pure abstract category is not super useful.
No, I understand. Okay, but so category repository plus the properties, the human defined properties. I mean, it's just like in axiomatic theory. We have the axioms, and then we have, well, we actually don't have. We have notable theorems, for example, but we could have constructs that are defined in terms of the underlying operators. That makes sense. I mean,
right. Basically, all of these are just constructions that are ultimately built up using combinations of like set builder, set union, like set theory constructs.
Yeah,
These are all definitions and theorems in set theory, the way they're done now.
I get it, but the basic point is that, sort of operationally, there'd be a category repository that contains also for these categories, just like we have like notable theorems in the axiomatic theory place. So similarly here, we would have sort of notable, interesting properties that will be defined in terms of the raw material of those categories. Is that right?
I think so. That'll be the hope.
Okay. And just to give me a sense of scale, in terms of the number of, I hate to ask these kinds of meta questions, but in terms of the, in typical pure math, are there like 100 categories that people commonly use? I mean, I know there are ones that I hear about repeatedly, but I mean, are there, if you don't, what's the rough size of this category repository?
My estimate, which is a very rough one, is that if we had on the order of 20 to 30, we could cover 95% of cases.
Okay. Fine.
It's mostly it's set, top, vect, group, ab, FD Hill. There are a handful, right? But it's not.
Okay. So it's comparable to axiomatic theory then.
I think so. I mean, it's much less diverse than axiomatic theory.
Because why?
Because almost all of these are really almost all the categories I've just described are concrete in the category theoretic sense, and they are all equipped with some faithful functor to set. So there, each one you can think of as being like set. So some forgetful functor to set. You can think of each one as being just set with some additional structure. Whereas axiomatic theory supports the aim was always to support a fairly diverse collection of axioms.
Right. So okay. So I mean, in terms of this project, it seems like a good next step would be to try and define that category repository.
Yeah, absolutely.
Okay. And then the end result of that would be that one should be able to enter some statement in terms of the properties that are defined in that category repository, and then automated theorem proving should be able to crunch through. Well, you should be able to both enumerate things that are true in a given category, and also you should be able to actually just find a path from one statement to other statements, and thereby, I mean, what does a proof look like in the category theory world? What is the presentation of a proof in the category theory world?
Oh, Wildcats has 29 categories. That's useful. Nick is pointing out. So
Okay.
Yeah, so 20 to 30 is probably not a bad estimate.
Good. Okay.
But no, anyway, so what a proof looks like depends on, there are many. I mean, but a large large class of proofs effectively boil down to these commutative diagram pictures, right? That you essentially just, you give some coherence condition, and the proof is literally witness, a particular collection of compositions of morphisms. You say these morphisms exist, and
how would we present that proof?
I mean, that's a separate question. I mean,
but can you
ideally
give a path or something to represent that proof?
Yeah, well, I mean, a composition of morphisms is a path,
right? But so
you'd be giving you'd be witnessing a collection of paths and relations between those paths.
I'm going to go ahead and stop sharing.
Okay. So just like with fine equational proof, where it's a little bit, unclear, and hopefully we're working towards having a better, truly computable representation of the proof object. This again is a little bit meta in terms of what the proof object is. Is that a fair statement?
Right. I think so. I mean,
okay, but that's fine. I mean, but the important point is, in this case, one can both enumerate everything that's, one can just start grinding out sort of everything that's true, and that reminds me a bit. Well, I mean, obviously we've done that for these equational kinds of things, but isn't it in our geometry project? Don't we similarly have okay, let's just ask the question, the kind of proving that's going on here, how does it relate? Maybe Ian can say this, to our geometry project. Or is that totally a different idea?
So there's currently no released proving in the geometry project. Peter Behrens is working on fine geometric proof, which is very similar to fine equational proof.
How does it work, roughly? I mean, does it turn things into algebra?
I'm not exactly sure.
No,
But it has
definitely
common
doesn't.
theorems like side angle side, congruence, and things like that.
Jonathan,
Peter's fine geometric proof essentially uses it's very much more like Wolfram Alpha show steps. It uses human readable, human comprehensible steps. It doesn't boil everything down to some automatable language.
Okay, fair enough. Okay. Okay, there are questions here about so first point is, with respect to this abstract category framework, you are fairly well advanced, although it doesn't look like you've started to do these monoidal category type things.
Well, I mean, abstract strict monoidal category currently does a lot of stuff. That's one I've spent a decent fraction of the last several months working on.
Wow. Those pictures are a little hard to understand. Oh my gosh, what on earth is all of this? Oh my.
Did those look familiar?
Yes. I don't understand them, but
they are bird tracks or Penrose blobs or ZX diagrams or tensor networks, depending on who you ask.
Well, that's very interesting.
So all of the Predrag's notation, Penrose's notation, all of the ZX calculus notation, they are all effectively special cases of string diagram notation in monoidal category theory. And so abstract strict monoidal category has a general way of manipulating string diagrams. So if these were morphisms in the category of finite dimensional Hilbert spaces, then we'd get exactly Penrose graphical notation. If they're morphisms in the category of Hilbert spaces in general, if they were in the category of finite dimensional Hilbert spaces, we'd get ZX diagrams. If they were in the category of, say, abelian groups and their representations, we'd get Bertrand notation.
Okay, so can you walk through roughly what on earth these are? Where's the simplest case of this?
Yeah, so all you're doing is you're taking a category and you're equipping it with a tensor product, right? You're equipping it with a monoidal structure.
Yep.
And so what that represents concretely is you're equipping it with a bifunctor. That is to say, you're equipping it with a functor from the product category with. So if you've got a category C, you can take the product category C cross C, like a sort of, which acts like a kind of Cartesian product, right? So you're treating pairwise objects and pairwise morphisms. And if you have a bifunctor, i.e. a functor from C cross C to C, that satisfies a certain set of coherence conditions, associator and left and right unitor coherence conditions, that effectively says the tensor product operation is associative and unital, it has an identity, then you get a monoidal category, right? So it's a category equipped with this additional bifunctor.
Okay, so here in particular, you've got this category set up. I think I love the fact that we can just type stuff in. It's actually okay. Great. Okay, so this is some category here. I think I understand what that is. Now you've got the product, the tensor product category. Presumably that's this category C cross C here. Is that right?
Yeah. So the left-hand side, so the left-hand side of that functor over there in input 25 is the product category.
Okay. And this maps down to a single copy of the category. Is that right?
Yes. So right now you can see it's obviously not equivalent to the original one. And that's a sign that right now this monoidal category is underspecified, that you'd need to impose some additional mappings between objects and morphisms in order to have this be a valid monoidal category.
Okay, so this is Y cross Y maps to Y, Z cross Z maps to Z.
Yes.
Okay. X cross X we haven't defined.
Mm-hmm.
Okay.
And then, of course, there are some equivalences that are defined purely by the axioms of category, by the axioms of monoidal category theory. So if you asked for associator equations and left and right unitor equations, you'd get lists of equations imposed just by the axioms of monoidal categories.
Okay, so here, this is a representation of this product category.
Right. So
And-
exactly. So
yeah.
well, it's a representation of the monoidal structure. So string diagrams were essentially invented precisely because the ordinary, when you start dealing with monoidal categories, the ordinary categorical diagrams become incomprehensible, right? They're way too large, way too complicated. So string diagrams are a way of nicely representing, decomposing the structure of morphisms in a monoidal category.
Okay.
So here you can see, so this is an association. So you can see, okay, F cross F is a morphism. And then you can see it maps to a list. And this is giving a list of all equivalent ways you could represent that morphism in string diagrams. So the first diagram there is saying F tensor F maps X tensor X. If you take the object X tensor X and you apply F tensor F, you get Y tensor Y.
Mm-hmm.
But you could also, but the remaining elements of the list are saying that's also equivalent to taking X tensor X, applying identity X tensor F, so you get X tensor Y, and then applying F tensor identity Y, and you get Y tensor Y. It's the same, same result.
I see. So this is putting in a thing in its inverse here.
Yeah. No, it's identity.
What do you mean? So but this little bead here on
Yep.
this line is, I mean, why couldn't I not put 3 beads on the line as well?
Oh,
Or can I?
you could.
Okay, so this is just the first level of one level beading, so to speak.
Yeah. Of course, you could compose in sequence as many identity operations as you wanted.
Okay. And this is showing.
So this
I
is showing
see.
for composition. So here you've got identity X tensor G compose F. And there's only one way of representing that here.
Wait a minute. What's the tilde thingy?
Identity.
What does that mean?
The identity morphism on object X.
Okay. All right. Fine.
It's the do nothing operation.
I see. So that's this piece here, and then F.
So yeah, so G compose F is just that thing, right? You're applying F, then you're applying G.
Okay, I get it.
And so if we were in the monoidal category of finite dimensional Hilbert spaces, then the tensor product structure is the tensor product of Hilbert spaces, and then each one of these boxes is just a matrix, and then each one of these wires is some vector.
Okay.
And then you get a ZX diagram.
That's cool.
And then, so if you scroll down, you can see there are, here's a non-trivial example. Now you've got actual kind of gluings between stuff, right? So now in this version of the monoidal category, we've called F tensor F big F. And so now whereas before we had like 2-legged spiders, now we've got a 4-legged spider. You've got X tensor X goes into big F and it outputs Y tensor Y. And then you can plumb those together in various ways. And so you can build up, by taking these tensor products, you can build up spiders with arbitrary numbers of legs, and you can do index contraction. And essentially, so strict monoidal category also includes as a special case, essentially just a general method of manipulating tensors, like abstract symbolic tensors.
But so what's happening here is you had previously that outer, that pure product, and this is now saying, this is a mixing thing that is combining these elements, right?
Yeah. So if you scroll up just a little bit, you can see how it's defined. So here in the definition of the monoidal category, we've said, F tensor F goes to big F, G tensor G goes to big G, etc.
Okay.
And that's what's being reflected there. And so then you can once you've got these spiders with more than 2 legs, there are different ways you can plumb them together.
Okay. And so this is ultimately going to So, well, this is interesting, and I'm lovely, and I need to understand it. But when we think about this concretely, where these functions F and G are actual, Wolfram language functions.
Yes.
Is this a way? So
the monoidal structure is what turns multi-way systems into single-way systems, right?
Mm-hmm.
Because effectively what you're doing when you take a monoidal product is you're saying, okay, we've got these two computations that could be performed in parallel. So, okay, suppose you've got the situation where you've got some multi-way system, you've got a branch that takes you from X to Y, and you've got another branch that takes you from Z to W. You could think of that, you could apply those two branches in parallel, those two evolution edges in parallel, but you could think of that as being a single operation applied to X tensor Z, which then yields Y tensor W.
Right. So it's almost like, I mean, these things are, if the things were like this, where they're running separately, so to speak, there's no synchronization defined for those. They're just separate things. Whereas here, you're saying they have to go into this mixer and be processed together to produce a result. Is that right?
Right, exactly. And so in terms of the multi-way structure, this is precisely what gives rise to things like entanglement, right? This is what gives rise to non-trivial branchial structure.
Yep. Okay. So, but what does that mean? Okay, so let's say we're doing parallel computation.
And again, by the way, I again want to plug this. I think this is not a terrible way of doing symbolic. I know there's like disagreements about how symbolic tensors and things should be handled. I think this is not, but I personally think this is not a terrible way of doing it.
What does it? What's the it here? I mean, so we've got tensors, T alpha beta gamma.
Yep.
Times U beta gamma epsilon or something.
Right. So each one of these blobs is a tensor, right? Every input wire is a contravariant index. Every output wire is a covariant index. And then the rules for how they compose are precisely which strict monoidal category knows and has the ability to manipulate are just the rules of tensor algebra. Right. So index contraction is taking one of these wires and plugging it into it. If you contract along the first and third indices or something, what that means is you're taking the third wire, which will be an output wire, a covariant index, and you're plugging it into the first wire, which will be an input wire, a contravariant index.
Right. By the way, a practical point is that, I mean, these, in terms of these graphs, this again requires labeled ports in these graphs.
Right.
Which we still don't really have. I mean, maybe Roger can comment on this. This is yet another place where we're going to need that. Oh, Roger disappeared. Okay, but so in terms of thinking about this, and we should wrap up for today soon, but this is really, really cool. Really cool. Okay, just if we think about these as actual concrete functions.
Okay.
I mean, look, tensors, there's a concrete, go ahead.
Should I share and just show the concrete functionality?
Yes, please do.
So what's your favorite function on let's say your favorite multi-way system on numbers?
2 hash 1 plus hash.
Okay, so let's do let's run that for 2 steps to begin with. Okay, so this is now a way of, rather than specifying the arrows of a quiver directly, right? This is a way of generating arrows of a quiver as just a multi-way system, right?
Okay.
So we're taking, 1 plus hash applied to 4 or whatever. And then we can take this and we can use that as the basis for, the skeletal basis of a category. Maybe that's okay. Let's do 2 steps to begin with to make it a little bit easier. So this is now the category form of that. If we ran the same multi-computation for 3 steps, we'd get a more complicated looking category structure.
What answers are we going to get here? Is it going to be the same? Because this is, oh gosh, what are we seeing here? Is this?
I mean, this is just the multi-way system, isn't it? Maybe do the reduced.
No, because it was the transitive closure of a multi-way system. I mean, usually in our multi-way systems, we're showing the transitive reduction.
Right.
We could show the transitive closure, okay, which is what you would do.
One nice thing about this is, for instance, we could take that and we can say, just like we can. So all the functionality from abstract category carries over into concrete category, along with some additional stuff. So we could say, what are the commutativity equations? So these are now statements in Wolfram language that effectively are correct, statements about correctness of function composition, right? So if I took this, I think if I just say activate, yeah, there you go.
Wait, are the left and right sides of those equals just composition, or are they actually? Oh, they're actually applied to things like of one and so
Yeah.
on.
Exactly.
Well, they're applied to the initial condition in the end.
Right. I mean, again, you could specify multiple initial conditions if you wanted. So
Sure.
Just for visual sake, could you try doing getting one of the reduced graphs?
Yes. Although, I mean, wait, do you want reduced or do you want simple? I think.
I think I want reduced, just like the transitive reduction.
The reduced labeled graph is going to be the same because there are no equivalences. But what you could do, what you may want is reduced by these commutativity equations. So if I do that.
I meant more if there was a way of visualizing the transitive reduction. I mean, in categories, do people always draw the composition edges, or do they?
But the transitive reduction is the transitive reduction is the quiver.
Oh, I see. Okay, yeah, sure.
And
But
so
yeah, go ahead.
You can always get the underlying quiver from any category.
Is the quiver always? The quiver isn't always minimal, though, right? Like you could have, or is it? No, I guess the quiver doesn't know. You can't specify in one of these quivers that this edge is the composition of these two other edges, right?
Right.
Okay, fine. Yeah,
you can't.
So there's no canonical minimized form, is what you're claiming.
I don't think there can be, because you to do that you'd need to have a notion of composition on the arrows of a quiver, which you don't have.
Okay, so in other words, okay, but so now, all right, so this is.
So one of the fun things about this is that then means that we can use the automated theorem prover in the the sort of mini automated theorem prover in abstract category. We can use that to prove theorems about Wolfram language functions, Wolfram language code. Like in this case, it's a pretty trivial collection of theorems, but you could imagine proving kind of some more interesting things involving universal quantifiers and stuff like that.
So wait a minute. So we've got morphisms here, which are just random functions. I mean, in this case, 2 hash 1 plus hash.
Well, they're not the morphisms; they're the generators of the morphisms, right?
I see.
In this category, the morphisms are pure functions that can be constructed by arbitrary compositions of those generators.
So, okay, so that's sort of a multi-way. Okay, so that's like, this is multi-weighing with the generators F and G, so to speak.
Mm-hmm.
Just like we could nest list with the generator G or F or something, right?
Right.
And now, but you're saying a program. Are you saying that there is the analog of a program, an arbitrary program, as opposed to a nest list constructed program that would have these different arrows labeled at the programmer's whim, so to speak?
No, it's more that a program. So I mean, essentially, you could imagine building each one of these. One can think of as being a subcategory of some category of Wolfram language expressions whose morphisms are pure functions. Right?
Well, sure.
And the point is that any arbitrary program is just an edge in that graph, right? Any arbitrary program is just a Any functional program is just an edge in that graph.
Well, in the graph, wait a minute. This is an infinite category of Wolfram language expressions. And
Yep.
You're saying when we draw this diagram, every possible transformation corresponds to so that transformation might involve huge amounts of gnashing of teeth to get from one expression to another. But in this rather traditional mathematical way, we're just saying that's a morphism, boom, it happens.
Right, because the transitive closure essentially hides all the details of the computational complexity.
Right. I mean, transitive closure is the enemy of computational irreducibility.
Right. Right.
Um.
Hence James's summer school project from last year.
Right. Okay. But so we could imagine something where we have restricted the set of morphisms to not be arbitrary programs, but to be some subset of programs.
Right.
perhaps generated in some way like the ones here.
Mhm.
Now, one question then is, functors between those morphisms. Do we have any idea what on earth those are?
Well, there are two levels of that question, right? There are higher morphisms between the one morphisms, and there are also functors between the categories.
Fine. Okay, so the higher morphisms between these morphisms are essentially equivalences between programs.
Not necessarily equivalences. I mean, this is one of the reasons why I was kind of interested to see what James was doing with N machines, right? Because that's kind of, from my limited understanding, that's what an N machine is. It's supposedly some way of translating from, a pure function in this category to another pure function in this category.
James, can you say something about that?
I'm still not I'm not treating it necessarily categorically. It's more of taking univalent foundations and just focusing on the programs part and having a way of computationally treating higher homotopies between programs in the Roolead, basically. And that's something that Jonathan and I should discuss, is how to, the extent to which it should be made categorical. Because I even think in foundations of univalent foundations, there are kind of different degrees to which people actually explore the kind of category part of the trinity, so to speak.
All right, so I'm still.
But the point is, I think Jonathan's point is that there's a difference between functoriality and, say, homotopy equivalence, for instance. Those things are distinct.
And gosh, there's a lot of complicated.
Or just between, there's a difference between functoriality and equivalence as well.
Well, look, all that I'm saying is that there's a difference between compilation, which is what the functor is, and program-to-program transformation, which is what the higher morphisms are. I'm not saying anything particularly more fancy than that.
Okay, compilation or interpretation being from one category, from one class of expressions to another.
So you could imagine versions of these concrete categories for different programming languages, right?
Or for Turing machines versus cellular automata.
Yeah, exactly. Different models of computation, and if they're all equivalent as models of computation, then at the very least they should preserve compositional structure.
Sure.
Which means there should be homomorphisms between those categories, i.e., there should be functoriality. That's really what compilation is.
Although seeing that explicitly, it will be a little bit more fancy than that, because there'll be things like, the representation of states, there'll be questions about equivalences between different representations of states, where two states might have different forms, but they might be equivalent, et cetera, et cetera, et cetera. I think it's a little bit more tricky.
Oh, sure. No, this came up in the summer school a bunch of times about, like, state equivalence is kind of a really crucial thing in these, what your state equivalence function is a very, very model dependent, or what the reasonable state equivalence function is a very, very model dependent question.
Yeah, and no doubt observer dependent also, because that's ultimately what, at some level, every multi-way graph is just a tree if it wasn't for state equivalence.
Right.
But okay, just trying to map out objectives here. This thing with Wolfram language expressions, do we imagine, okay, what is the evaluator in terms of this? I'm just confused about how this fits in to how we think about, maybe, does Nick have any thoughts about this? Nick has been working on some related multi-computation ideas. Perhaps not.
Well, those generators are like any rewriting rule. You can, yeah. So all computational models can be looked at those generators. Doesn't have to be a pure function. It can be just applying a rewriting rule.
Yes. But my question is, how does this fit in? If we were going to go ahead.
It has to be a pure function in the sense that it can't have side effects. If it has side effects, then your function composition is not necessarily associative.
Sure.
And
Is that in Wolfram language it's more natural to look at computation as just rewriting and not applying a function, because rewriting is even more pure than actual pure function.
I don't disagree with that.
Right, but so how would we use this? What would be and how, in terms of, okay, so let's say we have models that are multi-computational models can we use this to understand more about those models, or
Sure.
where does this get used? Yeah,
Well, we can use it to prove theorems about them. We can use them, you can take some multi-way system and you can actually generate the monoidal category that it corresponds to, and you can do reasoning about that monoidal category, and you can do tensor manipulations in that monoidal category. And
so what's an example of something you might conclude from that?
I mean, that's a very general question.
Well, I mean, like, for example, you might prove some theorem that, I don't know, the branchial space is always bounded in some way or something. I don't know. I mean, what types of things could you imagine establishing?
Well, I mean, for instance, establishing that, for instance, a given multi-computation generates a monoidal category with a certain dagger structure, or that has compact closedness, or that a particular graph rewriting rule generates a topos, or what. Like, I mean, these are all things that are obviously interesting and relevant to a bunch of physics project stuff.
Indeed, very much so. So what do you mean by proving that it generates a topos? What would be the sort of payoff from that? I'm asking these really naive questions because I'm still struggling with this whole area. But go ahead.
Well, I mean, if we can show that it generates a topos, then we can show, for instance, that it's a reasonable basis for metamathematics. I mean, that's one obvious thing. Another thing is that if we can show that it's a Grothendieck topos, then it means it has a spatial structure, and that means that if we have a way of proving that, then it's a way of getting spatiality without the need to prove that a continuum limit exists. Yeah, there are lots.
So how plausible is it to do those kinds of things?
I think quite plausible. I mean, right now we like in the currently rather embryonic implementation of abstract topos, there is code for for testing and proving whether an arbitrary category is a topos.
Sorry, I got distracted for a second. Could you say that again?
So, I mean, I have an embryonic implementation of abstract topos, which builds on the abstract limit framework, that has functionality for determining whether an arbitrary abstract category is a topos and proving that it is, if for actually witnessing the finite limits and actually witnessing the subobject classifier in the case where it is. So I think it's quite plausible. I mean, essentially the code already exists. It's just not deployed yet.
There's a lot of cool stuff here. All right, we ran way over time. I'm still not fully absorbing this. I think maybe I have to actually play with it to absorb it some more. I mean, it doesn't help that there's just this giant, festival of weird epimorphism, retraction, whatever things that I don't know why one cares about, so to speak.
I mean, just for context, I mean, all of those things are basically taking standard intuitions that one has about functions and, making them work in the more general context of morphisms, right? So epimorphisms, monomorphisms, bimorphisms are just essentially the notions of injectivity, surjectivity, and bijectivity.
Yes.
Fractions, sections, isomorphisms, just left-right inverses and left and right inverses.
Yes.
Etc. I
mean, yeah. Okay. Other comments from people here about sort of how this fits into the bigger pictures.
I mean, just
sorry. Here's a naive question. It's like when you have, instead of generators, you have a hypergraph rewriting rule, and you get a concrete quiver from those. Would it induce a hypergraph category with all those spans, cospans?
That's an interesting question. Yeah, so probably not. So hypergraph categories are not categories of, as you're aware, like hypergraph categories are not categories of hypergraphs. They're monoidal categories whose string diagrams are hypergraphs. I don't think it's a priori obvious that the category generated by a hypergraph rewriting rule would necessarily be a hypergraph category.
Yeah, probably.
I think it's a name collision.
Mm-hmm.
Every pun is going to be proved.
Yeah.
Anyway.
What I was going to say was, I mean, the main reason I wanted to have this meeting was it feels like, there's the pure math packlet, there's the multi-computation stuff. There's also, I mean, I don't know what the long-term plans for graph rewriting in the language are, but for instance, because we have things like pullbacks and pushouts, we can construct push-out complements, we can build DPO systems in this framework. And so again, like that's if there is going to be a general implementation of graph rewriting in the language, it feels like that should probably be integrated. So and as I say, there's there's the implementation of these monodal categories. We've got these string diagrams that are really just ZX diagrams. They're really just for the case of FD Hilb, they are just specifications of quantum circuits. So it feels like there's potential integration there. And my concern is I don't want to develop these things too far, but without at least touching base about.
Like, no, I agree, because it'd be nice to have this as a foundation, for thinking about all of those different kinds of things. But it would really be helpful. Something that I'm just not getting right now is, how you think about, this is, look, one thing that I have long considered, really long considered, ridiculously long considered, is how do you turn graphs into functions?
Right.
And by essentially making their edges do something.
Mm-hmm.
And this is a version of doing that.
Right.
And in a sense, a lot of the fancy stuff that's going on here is things like, how do you think about composing, functions represented by graphs and stuff like this, I think. And that's essentially how do you think about taking products as in tuples of
right. Yep.
Functions represented by graphs.
It's an irritating quirk of terminology that product categories and categorical products are very different things. Product categories are like the tuples case. Categorical products are these weird universal property things that are unrelated.
Okay. Does anybody else have anybody else want to offer?
Yeah, can I ask, do you have a way of getting the terminal objects in a category?
Yes.
Implemented?
So in abstract category, we build a category with a terminal object, x, y. Y is a terminal object.
Cool.
It's also a strict terminal object, and etc.
Yeah. So one idea is that things like fold can be characterized as morphisms from an initial object in a category that's defined by an endofunctor. It's the idea of catamorphism, and the dual of that is nest, and that's basically what I used to understand nest tree and treefold. So I think I'm going to explore that a little bit.
So you think, your implication there is there might be generalizations of those things that are sort of evaluation operations on graphs, for example.
Yeah. So there's like the category of Wolfram language patterns. This is like above you have like the objects are particular expressions. I was thinking about the case where the objects are patterns, and the endofunctor that I'm referring to is the idea of like a function signature. So for example, tree takes two arguments, the data and a list of trees, and that can be expressed as an endofunctor. And from that, you can have a constructor basically for trees by having, you look at the terminal object, the final object would be like the object that represents all possible trees. And so you can, nest tree is basically the thing that constructs the morphism to that final object, and treefold is the thing that starts with the initial object, which is trees, and applies an operator. So I wonder if there's a way to generalize that.
Yeah.
Yeah, that's kind of interesting.
I think Haskell have all these type classes. When it derived foldable type class, traversable type class, when it all comes from some functor type and monoid type classes. So it's basically a generalization. So all of this kind of nests and folds can also be derived like this.
Like what?
Well, just Haskell people like this stuff. They all like category theory and to define their functions and type classes. And they have this special type classes for foldable data structure, traversable data structure. And they basically do similar stuff there.
Okay. Okay, anybody else got comments? Christopher, Mano, James?
I don't think so.
I did just want to mention actually one other in terms of the applicability to the multi-computation stuff. Okay, hang on. For some reason, this documentation page is loading extremely slowly. There we go. Is we do have support for vibration checking. I mean, so actually, it's one of the things I kind of wanted to work with Mano on at some point. Is getting the vibration stuff more fully featured. I'm sure I have. Yeah, here we go. Okay, so here we have a way of determining. We can test whether a given functor is a valid discrete vibration of categories. We can actually compute what the individual fibers are if it is in the case where it is a Grothendieck vibration, etc. And so there are situations where, for instance, we could actually go and concretely prove for a given Rulio multiway system that individual multiway systems correspond to specific fibers. That the decomposition into individual of a Rulio multiway system into individual multiway systems is a valid Grothendieck vibration. That's also something which in principle would be supported by the abstract functor framework and the concrete functor framework as it's currently developed.
So it seems to me one thing would be useful here. I mean, this is more of a research type thing, as a lot of this is, I mean, just taking some things that we've done with string multiway systems and just seeing how that works in the setup, or seeing what one can establish there.
Mm-hmm. Sure. But as I say, the nice thing is that a bunch of these kind of currently a bit more loose ideas about fibrations and foliations and things in arbitrary multiway systems, we can actually, once we have a way of representing concrete functors, we can actually just go and explicitly compute, what are the fibrations.
Yes, I understand. I think I need to understand this better. I think I need to crunch on it a bit, and then we need to have another discussion, because I mean, look, design-wise, this looks reasonably nice. I mean, quite nice. I had micro comments like, you shouldn't call something blah 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 or objects or whatever they are, and then have a list of things that say F arrow true, G arrow false type thing.
Yeah, I mean, it's the
maybe that's more like the indicator or something, or it needs a name that is, because it's basically like a set where you're giving an whatever they're called, indicator function on the set or something.
I agree. So, I mean, right now, the fact that, say, monomorphisms returns an association whose values are Booleans, I agree, is kind of weird. I initially thought about calling it like monomorphism Q or something, but that seemed even more...
that's even more bizarre. I mean, monomorphism information is also rather silly. I don't have an immediately better suggestion. I mean, it is, if I understand correctly, in set theory, that would be called an indicator function.
Yes.
Is that right?
Yep.
Not that that's necessarily a good name. That's one thing I noticed. I mean, other than that, it really looks quite, and the visual appearance of these diagrams.
Yeah.
And I think, things like that composition operator, does have to be somewhat standardized, because that composition operator is going to get used all over the place. And it's going to get used, if I understand correctly, it really should be something which can be interpreted as an actual composition operator in the case of orphan language functions.
Well, I mean, that's why in the concrete category case, we do actually use, where is it? Yeah, we do actually use @star.
I see. So, but the concept is that there's kind of an abstracted @star, and then there's you might claim it's a little bit like single equals versus double equals. And although I don't know whether that's really the right way to think about it, one of them is a kind of an abstract composition, and the other is an actually do it composition.
Yeah, I would think of it more as like the formal operators that we use in axiomatic theory. Right?
Yes.
It's like you have plus, which actually has semantics, and then you have some kind of formal plus, which is just defined by some algebraic axioms.
Yes, which is not a super satisfactory dichotomy.
No.
But I mean, so this has that same issue that it has the. I mean, in a sense, like in axiomatic theory, we have sort of this notion of, maybe we don't actually. We have sort of, yeah. I mean, we could have sort of the common interpretations thing somehow in the category. I don't know. That maybe makes sense. All right, there's more to figure out here. I'm supposed to go to some completely different meeting, but this is really very nice stuff. It's great. I mean, so there's a lot of these things that are already in there as function repository, as released function repository entries, and there are others that are in the works. I really think it would be useful to start thinking about this category repository, because I think that will give you the ability to have many good examples here. And
Right.
also the ability to understand. So it seems to me like encoding the first few of those categories, set, top, whatever else. I do love the way that, in a, oh no, we're not doing computation here, the category theorists name their things after kind of primitive variable names.
Right. It does rather beg the question of whether we should use wolf to denote the category. I mean, because in effect, this is some subcategory of the category of Wolfram language expressions and morphisms.
Yeah, we should call it wolf, just in order to fit in with the absurdity of the I like that idea.
Because ordinarily concrete categories were defined over sets, right? You say a category is concrete if it's an abstract category, but it also has some forgetful functor to set. But because sets are quite alien to the language, it feels much more natural to have this be the kind of the base category. Right?
Yes, I agree. But I think, right. But that means that in the category repository, we could imagine there are certain properties of the wolf category, so to speak, and there would be some categories that are mappable in this forgetful functor type way to the wolf category, like some sublanguages, like some particular provable thing with lists and reverse and take and first and last and etc. and append and so on. We can imagine some.
Right, exactly. And so you could even imagine. I mean, this would give you a kind of fairly systematic way of constructing fully formalizable semantics for fragments of the Wolfram language, right? You could imagine construct some, as you say, you could imagine building some fragment, for instance, based on list operations, where you could actually prove correctness, of all programs or something.
Yeah, those fragments won't be terribly big.
No, of course.
Okay, but I mean, so look at concrete things. The construction of the category repository seems like a highly worthwhile thing, and just like we have axiomatic theory, we probably need category data or something.
Well, one question is, should this be part of the pure math packlet, or do you envision something separate?
I think they should be sort of separate initially, but then expect to have cross connections and merging, because the pure math packlet already has lots of design that may or may not be consistent with this. Or what do you think, Ian?
From my end, I think that there's very few properties currently for category entities. So the design's pretty much wide open about what kind of properties you want categories to have.
I think for the sake of just the process of doing this, we should build it separately and then expect to knit it together.
Mm-hmm.
It's really rather exciting. I mean, because do we think we will actually be able to do practical pure math with this that is non-trivial, interesting pure math with these things?
I certainly think so.
So you think that the sort of exercises in a topology book might be doable with this?
Well, actually, I mean, that's one of the things that okay, it's one of the things that Yorick and I were talking about the other day about as a possibility of going through. I mean, we actually discussed that precise example of going through a graduate level like algebraic topology course and figuring out how we would encode like the exercises in this CT framework, because all the all the functionality exists to do that. And basically, most of algebraic topology at some level you can reduce to diagram chasing and homological algebra. And we have very good algorithms for doing that in the CT framework. So it, like, I don't know, I don't see any major obstruction. It's just there's a bit of translation that you need to be able to build that takes you from the topology concepts to abstract category concepts. But that's okay.
I just want to point out we did have an intern curate definitions and theorems for algebraic topology.
You said, by the way, Ian, you went caved. Hard to hear.
Sorry, I moved my microphone away and forgot to move it back. We had an intern curate theorems and definitions in algebraic topology.
Where are those results?
They're in the pure math packlet. But
has Jonathan seen those? I mean, that would seem like a great place to start for this.
Yeah, I agree. No, it's
you should look at them, but I don't think you'll immediately use the definitions and theorems to do the project you were just describing, Jonathan.
Sure. No, but it's useful to look at. I agree.
Jonathan, maybe you're about to have students and things who might be able to contribute to this.
Yeah, no, that would be the hope. That would be
right. You can feed them. I mean, anybody who's learning this stuff, this is probably a great way to learn it, is to actually do some of that curation and so on.
Absolutely. But yeah, I'm the reason I'm kind of optimistic is because this is, there's when you're dealing with proof assistants and automated theorem provers, there's a distinction between whether you want your prover to be axiomatic versus whether it should be synthetic, right? Like, what do you want things to grind down to the underlying axioms of set theory or Boolean algebra or whatever? Or do you want your prover to operate at a synthetic level where it's directly manipulating the relevant concepts? And the point is that category theory is a very, very good foundation for developing synthetic theorem provers. So, yeah. I mean, so is type theory. I mean, that's kind of the lean principle. But yeah, I mean, category theory is a pretty good basis for that. Because
wait a minute, what were you saying about lean? What?
Oh, well, I mean, so lean uses type theory for the same purpose.
Yes.
And in a sense, it's not normally how people talk about this, but in a sense, they're using the fact that there's this nice duality between type theory and category theory, that effectively every topos you can think of as modeling, as having an internal logic that is some dependent higher order type theory and vice versa. That's essentially what they're exploiting.
But the question of whether math, which kinds of math are more naturally represented in terms of categories versus more naturally represented in terms of type theory, can you characterize that?
Well, like I say, I mean, there isn't really a distinction because there's a pretty direct translation from one to the other. I mean, James already mentioned, or at least parenthetically mentioned, computational Trinitarianism, which is sort of the basis of this idea, right?
Mm-hmm.
That's one part of the Trinity, is that there's a direct translation from type theories to categories. Because for any higher order dependent type theory, you can build a topos whose internal logic models that type theory. So I don't think there is any distinction between what branches of mathematics are most naturally formulated in types versus categories, because they're really equivalent representations.
Right. Well, and okay.
And so, yeah, I mean, the idea would be, okay, if you want to prove something about topological spaces, in most cases, it's easier to work at the level of reasoning about continuous functions and, homeomorphisms and things than it is to reason at the level of, open sets and neighborhoods and the underlying axioms.
Sure. I mean,
yeah. Sorry.
Right. So one question is, I mean, from a science point of view, sort of bulking up this kind of stuff. So you've got, we've got the axiomatic level, we've got subaxiomatic levels, we've got this level, you're calling it sort of the synthetic level. And one could imagine the bulk synthetic level, just as we tried to explore recently the bulk axiomatic and subaxiomatic levels. So what is the bulk synthetic level?
Higher category theory.
Something like that. Well, I mean, I get it, like usually if you're doing theorem proving or you're developing a proof assistant, you don't care about the whole category, right? You care about a specific collection of paths.
Yes.
Whereas the bulk theory is the theory of the full category, I would argue.
Yes. Okay. Fair enough. But then, right, and there might be meta statements to be made about that go beyond the statements made about individual paths.
Right. And the point is, I mean, and this is kind of one of the ideas behind, which is one of the reasons why people get excited about homotopy type theory as a basis for proof assistance, is because it's in general a lot easier to if you're reasoning at the synthetic level, it's generally a lot easier to grind back down to the axiomatic level if you want to, than to go in the other direction, right? So
sure.
If you
it's not obvious that the swirling molecules will actually form themselves into vortices.
Right, exactly. But if you've got the vortices, you can always, look at them with a more powerful microscope. And then, so in homotopy type theory, if you start with a purely synthetic notion of a space, you can always go back, but you can always pass to the set of connected components or something and recover the underlying set theory. But the point is, you don't need to do that. You can reason just at the level of the space. And there's a similar thing that happens here.
Yes.
So if you wanted to, you could, if we developed a purely symbolic representation of top, which I think is quite, I mean, as we've discussed, I think that is quite feasible to do. Then at any point, we could always, in principle, grind down any theorem we proved into underlying axioms in terms of open sets and neighborhoods. But for the most part, you wouldn't care about that. You could just reason directly at the level of the category.
Yes. And there will be, but ultimately, there will be sort of undecidable things at that level, even though much of the formalism, including this whole compositionality idea, kind of denies the possibility of that. And in a sense, what one has to think about is math is ultimately hard in some sense. And yet somehow that hardness is being hidden here by, among other things, the compositionality assumptions. Is that a fair statement?
Yeah, I think so. Which is why it'd be really lovely to have a generalization of category theory in which the edges in the transitive closure are essentially tagged. There's some algebraic relationship that tells you if I compose this edge with this complexity and this edge with this complexity, we get a new edge with some other, with some new complexity.
Right, but what we'll see is if you do things in this very compositional way, and you set up, areas of mathematics. Let's say we set up number theory this way. Okay. It better be the case, that there are difficult problems in number theory, because otherwise, what would the undecidability of this of the solvability of some set of Diophantine equations? What would that show up? How would that undecidability show up in this formalism?
Well, I mean, the point is that because we're operating at the synthetic level, there are two places where undecidability can show up. One is in the construction of the morphisms themselves, because remember, if we have a purely symbolic description of one of these categories, then even constructing those more, if you recall the kind of symbolic description of top that Ian was showing, where, you have the is continuous function or whatever, determining that, i.e. determining whether a given morphism exists between a pair of objects is itself a computationally non-trivial operation. So even building up the category structure itself can be undecidable. Then once you're at the level of the category, because the morphisms themselves don't, because the whole idea of being able to take transitive closures, being able to do composition is itself a kind of idealization, a non-computational idealization, you can also get undecidability creeping in at the level of, well, if I take this infinite composition of morphisms, unless I have some very, very nice computational complexity theoretic properties that mean that the complexity of the composition converges to some finite value, I can end up in the situation where taking that composition is itself undecidable.
Yeah. I mean, I would kind of think that in the standard formulation of number theory, the first place would be the place where things would get all messed up.
Well, my view is a little different. I would say that because the majority of undecidable problems, or I should say independent problems that have been discovered in mathematics have been kind of engineered in a very logician-esque way, right? They're things like the continuum hypothesis or whatever.
Yeah, except not the Diophantine equations.
Right. Well, exactly. But there are some which seem much more like natural mathematical problems and where you can also prove undecidability. Mm-hmm. My conjecture, based on just maybe this is bad meta-mathematical intuition, is that the former, the kind of apparently engineered logic-y ones are cases where the undecidability is creeping in at the microscopic level, i.e. at the level of actually constructing the morphisms. Whereas the more naturally the seemingly more naturally occurring undecidable problems are ones in which the undecidability is creeping in at the level of the morphism composition, because that's because it's at the level of the morphism composition that most mathematicians actually work, right?
Well, okay, so your statement there would be the natural ones are ones which you get by taking standard building blocks and putting them together, and you have to have an infinite number of those building blocks to get to the answer or something. Whereas in the other case, you're saying you have exotic building blocks, like, you know, the compilation of this statement is unprovable type thing.
Right, exactly. And my basis for saying that is just that, you know, if category theory is like the fluid dynamics and, you know, axiomatic mathematics is like the molecular dynamics, most mathematicians work at the level of the fluid dynamics, and it's only magicians that work at the level of the molecular.
Yeah, no, that's a reasonable intuition. This is really interesting. I mean, it's still, yes. I mean, the other part of this is kind of from a language design point of view, understanding the stuff about what on earth, this thing about graphs as functions and transformations between functions and so on, which I still don't understand. But this is, and I really think this formalism is going to force this non-compositional view, maybe more quivery view of what's going on, because of the fact that you're just sort of assuming answers in many, as we've said many times here, compositionality, assumes computational reducibility.
Right.
Sure.
Exactly.
Yeah.
I mean, in a sense, like you're assuming when you take some big composition like this in a concrete category, you're assuming that you can work out what the endpoint is.
Yep. Right.
Yeah.
I mean, one concern I have there is there's all kinds of, irreducible and multi-computationally irreducible computations, when we're just dealing with basic ruleyology or the Ruleyat. And that's where at least end machine theory is supposed to make this contribution, where you're studying within, bounded time frames, the merging and the translation between these different evaluation paths, even if you don't know ultimately what these paths end up yielding, either behaviorally or whether they terminate, et cetera, et cetera. So there's some sort of dance between the reducibility you can yield and the bulk statements you can yield with category theory, where you actually get end results, and in terms of ruleyology and the study of the structure of the Ruleyad, when you don't know. I mean, some of these rules are, they don't end, right? But being able to say something intelligent about higher equivalences, at least with time boundaries between these different evaluation paths. That's the kind of distinction.
To me, it's like there are many in computer science, basically, there are many cases like finite state, finite automata, where things have been simplified enough that they're decidable and that you can do things with them. My guess is that category theory is another such example where things have been kind of simplified enough you can, and it's very useful to have these things where they are decidable, because there's lots of engineering that can be done with them, et cetera, et cetera, et cetera. They're not the ruleyological in the wild version of things.
Sure. They're well-developed colonies within pockets of reducibility.
Right. But it might very well be the case that if you sort of remove a few assumptions there, particularly compositionality, then then suddenly the whole framework becomes much more computational and gets much more elaborate. And so just like in a finite automaton, the finiteness of the finite automaton, you take a Turing machine and you make it a finite sized tape, you'll have a finite automaton. And in this case, the compositionality is some kind of infinite claim. That's some kind of analog of finitization for like a Turing machine going to a finite automaton. But it is an infinite, it's some kind of less finite version of finitization, would be my claim.
You said compositionality is less finitization than something that's finite. What? Because you're composing different things together?
I'm not sure. I mean, it's because you're talking about categories that could be infinite categories, for example. They have compositionality, yet the category is infinite. Whereas in the case of a Turing machine with a finite tape, everything is finite there. That's why I'm saying that. In other words, you've got infinite numbers of objects, but you still have sort of finiteness. I don't know.
You're saying it's infinite in scope, but because ultimately everything you're working with is reducible, that you're able to make some kind of statements that are still infinite statements, but they're still ultimately these kind of computationally reducible statements because of their components.
Yes, that's basically what I'm saying. So I mean, I'm sure there's an analog of that in, for example, arithmetic and fragments of arithmetic, where you still have an infinite number of, I mean, any of these simplified versions of arithmetic, whether it's, Presburger arithmetic or whatever else, simplified version of arithmetic, you've still got an infinite number of integers, but there are, the statements you can make about them are always decidable.
Right. I'd like to see this, computational version of category theory. I mean, I think Jonathan has kind of hinted that this was something that I was originally going to work on, but I think I've become much more interested in the kind of releological computational on the wild side. I think the end machine thing, I think it's ultimately going to be different from this kind of computational version, computational complexity version of these categories, just because I think that as we're discussing, no matter what, those are going to have to be trackable. They're going to have to be computationally reducible. So I think they'll be slightly different, but it'll be interesting to see how we use both of them together to be able to speak computationally to pockets of reducibility and irreducibility, where when it's reducible, you can use category theory in order to have, a kind of strong actuarial, view of what's happening.
I need to run. I'm super late to something else here, but this is great. Let us continue. And seems like we have some different directions. Jonathan, you feel this is we've got a path here?
Yeah, I mean, what I was kind of hoping to get out of this meeting was more of a sense of, I mean, what I would like is to be able to have a very concrete bridge that says, that allows you to convert very neatly between concrete categories, multi-way systems, specifications of quantum circuits, possibly symbolic tensors, etc.
Yes, I think this was the introduction to that discussion. Right. Because I think that's a pretty complicated thing. Mm-hmm. And I think what we need to do next time probably is to take all those things you're mentioning and somebody present briefly about each of them.
Right.
And then let's see how similar or not the formalisms actually are.
Okay.
Because I think what you're doing, you were stating things here with respect to the way that you construct these categories and so on. You're stating these things very much as, here are the building blocks. You're basically giving these lists of how to build things up. And I don't know how similar that is. Again, there are these different things that they're probably all fairly similar, but we need to, next time, let us plan. I don't even know who's, I guess Kristen is project managing here. Let's plan to get if we can get a precise analogy, just an example where we can look at it like that numerical multi-way system, for example, if we can somewhat look at something like that in all of these different presentations, that would be helpful. I don't know whether that even makes sense for some of these other things. But it's like, how would you think, or pick something else where we can have a sort of a common thing to look at. Maybe it's a more abstract version of this with F's and G's.
And one just kind of practical point. So this was originally, still is, this meeting was included as kind of a design review. I don't think I saw an agenda until today. So I was basically prepared to talk about colors and fonts and stuff, right? Because it's a design review. So whatever we plan for next time, can we get an agenda just so we can kind of prepare and
I think Kristen should try and pull that together.
Yeah, just so we can enter the meeting with some idea of what we're actually going to discuss.
No, that was my fault for not preparing an agenda sooner. That's Kristen.
Well, but
and I didn't do it.
It's not just you. It's also, this thing was just called a design review, which I thought meant we're going to discuss angles and arrowhead sizes and just design details.
Right. All right, we should wrap here. Good stuff. Very nice to see all of this stuff from Jonathan.